Alright, so the first 4 slides are just review from the chapter or what we've done the last couple of days. So what you want to do is probably we'll actually pause the video, try them, and then just check your answers. If you've already done that, hopefully, then you can just see how you're doing. But these are things that these are old AP questions, old test questions that you can kind of see how you're doing. So you can see for the first one, you're just predicting entropy. So for letter A, you definitely have less because you lose a gas. Letter B, you have more because you have more gas produced, more chaos. Letter C, you're losing moles of total gas because you can see here on the left we have 10 gas moles, but on the right we only have 7. And on letter D, we also have less because we lost some freedom here. Second one is just calculating actually an entropy. So you do your products minus reactants. Make sure you multiply them by their coefficients. And you should get negative 207.2 joules per Kelvin. And again, feel free to pause this if you need to look at something or write something down. Third one is just writing actual equations. The one here is, the very bottom one here is hard because they're asking you to predict the missing particle, and there is a positron, and if you read your book, you know what a positron is. Positron is a particle that looks like an electron, except it's positive instead of negative, so that's kind of an unusual one, but again, it's not something impossible. And the last one is one of those real simple half-life problems, so just make sure you can figure out, okay, how long is that going to take? Okay, it's going to take 4 half-lives, and then you need to figure out, okay, if each half-life is 27.8 days, how long is that going to take me? So the last thing we're looking at here is Gibbs free energy, and what Gibbs free energy does is it actually predicts if something will happen or not chemically, which is a pretty powerful thing. We've never done this before where you can actually say this will happen or this won't happen. Alright, so we've talked about before what is entropy and what makes things more likely to be spontaneous, and we said that if you're exothermic, then you're more likely to be spontaneous. However, endothermic reactions do happen, and that they occur. So we don't really understand why. How does this happen? So what we found is that there's 2 major situations that affect spontaneity. The first one is your enthalpy, which is your exos and endos, and the second thing is spontaneity. So those 2 together combine to form the #1 reaction ever, which is Gibbs free energy, and that's what we're going to use for this thing. When they say is something spontaneous or not, this is how you know. So Gibbs free energy basically tells you how much energy is being available to the system. So this is the overall equation, but we don't actually use that one. This is the one we use. So we have delta G equals your enthalpy minus your temperature times your entropy, which can get confusing. Your delta G is always in kilojoules per mole. Your delta H is in kilojoules per mole, and when you are given entropy or when you find entropy, it's in joules per mole Kelvin, so you need to make sure that you change that into kilojoules before you put it in. That is the #1 thing people forget about this, and they miss it on the test, and they miss it on the AP test. You can also find Gibbs if they give you Gibbs information, just doing products minus reactants, and you only do that when they would give you this information, if they actually gave you the delta G information. If they don't, they're expecting you to do delta H's and delta S's, that kind of stuff. So you just have to be aware of how are the different ways I can get Gibbs, and then how can I actually solve it from what they're giving me. Alright, so back to Gibbs here. Alright, so what does it mean for Gibbs? If Gibbs is positive, the reaction is non-spontaneous. So that means your reactants are favored, they are more stable, and nothing happens. In fact, the only thing that would happen is a reverse reaction would occur. So if Gibbs is positive, it's a no-go. If Gibbs is 0, you're at equilibrium, which means both are happening simultaneously. And if your Gibbs is negative, then you are spontaneous. That means your products are more stable and your forward reaction is going. Alright, so we're going to start doing some problems here. Gibbs free energy is also related to an equilibrium constant. You guys don't really know what an equilibrium constant is yet, but basically that's where we're headed. So this is useful, and you can use it here. R is 8.314. Your T is your temperature in Kelvin, and the K in the equation here is actually like a thing, an equilibrium constant. All you really need to worry about right now is if that K is large, that means you have lots of products. And if K is small, you have lots of reactants. So it's not so useful at the moment, but it will be when we get to the next chapter. So all we're going to do is just do some different problems, and you can just kind of see how they go. So I'm going to show you some different ways to do the different things that we're looking at. All right, so the first thing they want you to do is just calculate standard free energies. And free energy is Gibbs. And it says you're going to make a nitrogen monoxide from nitrogen and oxygen. They give you your delta H, they give you your delta S. So that's telling you how you're going to solve the equation. Excuse me. And they give us our temperature. So I'm going to use my Gibbs free energy that has enthalpy in it and has entropy. And what you'll notice here is I changed my entropy into kilojoules, which is very important. And then what you do is just do a plug and chug of your numbers, and what you do is you get a number. And what happens is you say, okay, is it spontaneous or not? And you're saying, is it spontaneous at this temperature? Because if you change the temperature, you would change your free energy here. So we get positive 173.3 kilojoules per mole, which means that it is not spontaneous. So actually the reverse reaction would occur. The nitrogen monoxide could break down, but we would not be a spontaneous reaction. I'm just going to show you the next one. You don't even have to write it down if you don't want to. I'm just showing you how they can make the problem longer. So this is the exact same problem, but they're asking you to do it in steps. And this is actually an old AP question. So this is what we just did here. But what they're asking you to do is first to calculate delta H. And you all know how to do this, products minus reactants. Then they're asking you to do delta S, same thing, products minus reactants, and then they're asking you to put that together to get your delta G. And then they're asking you, is it endo or exo? Is it entropy increasing or decreasing? So it's exactly the same thing. You will get exactly the same answer. It's just a different way of asking you the question. So you do delta H and you see that it's positive, so it's endothermic. You do delta S, you see it's positive, so you have more chaos or more entropy. And then again, you do delta G, and it's going to give you the exact same answer, but you're going to see it's also positive and it's non-spontaneous. So it's literally the same problem, it's just a different way of asking you it. Number 3 is just asking you to calculate delta G's. So what I did here is I gave you your delta G's for the different chemical species. So phosphorus has this delta G, phosphorus trichloride has this one, and chlorine has 0. This is a different type of problem because we aren't given enthalpy, we aren't giving entropy, so we're not using that equation. So in this case, since they're giving us this, we are going to use our products minus reactants. So I plug and chug my products minus my reactants, be careful with your symbols, and we get a negative 1,102.8 kilojoules per mole of reaction assumed. So that's the forward reaction. And then what they're asking us in part A is they're saying what's for the reverse reaction. So again, it's the same thing that if the forward reaction is negative 1,102.8, that means that the reverse reaction has to be opposite that, or positive 1,102.8. Alright, I think we're doing 3 more. 1, 2, yeah, 3 problems. This next one is asking you to predict something. So they're not giving you numbers and asking you to predict this. They do this a lot on the AP test. And they're telling us that the enthalpy change for the combustion is negative 2,220 kilojoules. So it's releasing heat. So we know that our enthalpy here is negative. And they're telling us, what do you think that delta G will be? So you have to think about this. We know our temperature is 298, so it's positive. And you have to think, okay, what does that mean for entropy? And what you have to look at here is your overall entropy. So we have 6 things of gas on the left, but we only have 3 things of gas on the right, which means our entropy is probably going to go down, which means it'll probably be negative. And what that means is it's going to be less negative. So we would think that the delta G would probably most likely still be negative, but the entropy is not. Basically, entropy is not helping the spontaneity. The enthalpy is, because it's exothermic, that's helping it, but the entropy is actually hindering this. And if you calculate it, you don't have to spend your time calculating it, but if you do, you get negative 2,108 kilojoules, which is less. So that entropy is actually making it less spontaneous because we have less freedom being given off. And I know it's kind of something you got to wrap your head around. It's not something that's easy on this one. This one here, they want you to calculate the equilibrium constant. So remember, the equilibrium constant is related to delta G. So the first thing I do here is I calculate delta G. So I do my products minus my reactants, and you'll notice that some elements have no Gibbs free energy, and that's fine. So I get my delta G is negative 33.3 kilojoules, and then what I do is I put this in to my delta G equation. Now, one thing you may want to star or mark or whatever, this equation, for this to work, this one has to be in the joules. Just because this R is in joules, so you have to do it to convert it. Or you can convert this R into kilojoules, it doesn't matter, but it's just a way of making the equation fit. So I put my negative delta G there, plug it into my equation, I undo my natural log, which is e to the, and you're going to get a very large number. And remember, if K is large, that means you get products. If K is small, that means you get primarily reactants. So this is indicating that we have a lot of a lot of products. And again, if you do this differently, you might be off a little bit with rounding, and that's fine because natural logs are very sensitive. So any rounding that you did differently than I did, you would get a very different number than me. And then the last thing I just think is super cool is you can use this to actually predict boiling points and all that kind of stuff. So when you're at a phase change, your delta G is 0. So when you're going from non-spontaneous to spontaneous, or you want to know what temperature something it becomes spontaneous, this is how you do it. But I think it's pretty cool that you can do this here. So we want to know what's the boiling point of bromine liquid. Again, we're assuming we're at equilibrium, which means we're stuck in the middle. So this is the temperature where we're going from spontaneous to non or back and forth. So what I'm doing is I'm saying that my delta G is going to equal 0 because of the equilibrium. And what I do is you find your delta H, you find your delta S. I'm just using ones I've already done, so you don't have to look them up. You would do like products minus reactants. And what I'm doing is I'm rearranging my equation for temperature. And what I find is that if I take my delta H and I divide it by my delta S, I'll actually get my temperature in Kelvin. So again, you just look these up like you have been in the whole chapter. You get a rough estimate of 59 degrees Celsius, and it turns out the actual boiling point of bromine is 58.78, which is ridiculously close and pretty cool. So this is a nice way to estimate when you change from spontaneous to non-spontaneous. It's also a way to figure out phase change temperatures. And that is it for thermochemistry. I know you're going to miss it.